next talk is going to be given by two faculty here at St. Andrews. First is Dr. Hooley, who's a senior lecturer in theoretical physics at St. Andrews. His primary research interests are in all aspects of the quantum many-body problem. Together with Dr. Patrick Greenough, who's a senior lecturer in philosophy at St. Andrews and an associate fellow at the Arcade Research Center. His primary research interests are in epistemology and the philosophies of language and logic, but particularly relevant to today's talk, focusing on the problems of vagueness and indeterminacy. And the title of the talk is Spontaneous Symmetry-Breaking.
Is this audible? Or am I audible through that? Excellent. Well, good morning, everyone. It's a great pleasure once again to have been invited to speak at this conference, and a great honor as well. So thank you very much to the organizers for arranging it. I mean, we all hate guests at parties who turn up early, drink all the booze, knock the furniture over, and then leave by 10 o'clock, having destroyed the place. But I'm afraid as far as this talk goes, I am that man. And Patrick is going to step in at the halfway point and do some tidying up. So the link between our two parts of the talk, which is really about spontaneous symmetry breaking, indeterminacy, and the relationships between these two ideas, is that both are in a sense cautionary tales. So I suppose what I'd like to do really in the 25 minutes that I shall take is to start off by discussing some simple examples of spontaneous symmetry breaking, first from philosophical tradition, then from classical mechanics, and then from systems which we would say were quantum mechanical. And then to give the standard explanation of how so-called spontaneous symmetry breaking is possible. And then to describe what appears to be an exception to this standard explanation, where it seems as if the standard explanation would tell us that symmetry breaking should occur, but in fact it doesn't. And this is the phenomenon of superradiance from atomic gases. And I will actually have very little discussion, because Patrick will have some discussion. But I'll indicate, before my time is up, just one possible answer to the question of why these are different. It's interesting in connection with the previous talk, because the answer I shall give is concerned with the nature of the end state, which is almost a statement about the target that the system is aiming for. And of course, we're very uncomfortable in talking about targets that systems aim for. I'm still uncomfortable about that, so I certainly won't commit myself to it. I should say at the beginning that I'm very happy with questions during the talk, in particular because I'll be presenting several examples, and so the time to ask questions if you don't understand the examples is at the time when the example is still being presented. It'll probably be a lot more fruitful to do that as we go along than to do it after both I and Patrick have spoken. So as a simple example of spontaneous symmetry breaking, consider Buridan's ass. Buridan's ass was not created by Buridan. It appears in Aristotle's On the Heavens, and may indeed be older than that. I'll quote a more modern form, which is, one has a donkey in between two perfectly identical bales of hay, and the donkey is hungry, but in order to choose which bale of hay to eat, there would have to be some reason why the donkey should pick one rather than the other, and because the donkey is perfectly symmetrically positioned, and the bales are exactly the same shape and exactly the same distance away, there cannot be a decision in this case, and the donkey simply starves to death. This was, of course, used by Aristotle not as a suggestion of how to kill animals, but as a way of ridiculing the sophist's account that the Earth is stationary because it's spherical, and so the forces on it all cancel out. And in a sense, what Buridan's ass is designed to make us think about, like Schrödinger's cat, is whether we really believe that the donkey will not go and eat one or other of the bales of hay, and if we don't believe that, why do we not believe it? So keep that in mind. Let me just say a couple of interpretive words about this example. So when I say that the situation is symmetric, what do I mean? I mean that there is an operation that I can do on the scenario which would normally make a given scenario look different, but does not make this one look different. So I can take the two bales of hay and I can swap them over. That operation would normally make the system look different from how it looked in the beginning, but in this case it doesn't, because the bales were originally symmetrically distributed. So that's an important footnote, which is that when we actually describe a symmetry, what we do is describe an operation that leaves the system in question unchanged. If I rotate this sheet of paper by 180 degrees, its shape is unchanged, but that's not true, for example, of this jug of water, because now the handle's over here. And my notes are upside down. Let's come a bit closer to mechanics and use an example that's often used in engineering more than physics, actually, which is the case of Euler's strut. So what we imagine here is that I have a metal cylinder. We assume it is perfectly cylindrical, so it has rotational symmetry about its central axis, and I put it on a very resistive table or anvil, and I press down on it from the top with something heavy. And I keep increasing the pressure. Now we know intuitively what will happen. At some point that strut will buckle under the pressure. That buckling is also an instance of symmetry breaking. Provided that the system with which I apply the pressure is perfectly rotationally symmetric, and the cylinder is perfectly rotationally symmetric, there is nothing that picks the direction in which the strut should buckle, and yet clearly it will. It also seems reasonably clear that if I run this experiment many times, the fact that the strut will buckle will be true in every experiment. The critical pressure at which it buckles will be very similar in every experiment, but the direction it chooses in which to buckle we would expect to be essentially random. And in a sense what this talk is about is that word essentially. Is this random? Or is this just some feature of nature that we could have described more carefully, but haven't? A third example that I'd like to mention is what happens when one cools a magnet. Now I'm interested in this because it's fairly easy to show using classical physics that permanent magnetism is impossible. And the argument for this is quite simple. In classical physics, magnetism is generated by circulating currents. In equilibrium, there should be no currents in the system, which means that a system in equilibrium should have no currents. If there are no currents, there should be no magnetism. So in a certain sense, for classical physics, the existence of lodestones was acknowledged as a puzzle. And the resolution of the puzzle is actually quantum mechanical, which is there's a second way of getting magnetism, which is from the intrinsic magnetism of fundamental particles, which is not generated by the circulation of an electrical current, and therefore can still exist even when the system is in equilibrium. So if I take a block of iron, which is standardly not magnetic, and I cool it to a couple of 100 degrees below room temperature, then I discover that it becomes magnetic. It spontaneously magnetizes as the temperature is taken down through a certain critical level, which is the same every time I run the experiment. And that magnetization is a form of symmetry breaking because, of course, when a system magnetizes, it has to develop a north and south pole, and it has to choose, if you'll forgive me an anthropomorphism, where in the sample that north and south pole should be. So it has to choose a direction that links the north to the south pole of the magnet. And again, this is very similar to Euler's strut in the sense that I can run this experiment multiple times. I generally expect the temperature at which the block of iron magnetizes to be the same. I generally expect it to be the case that it will magnetize every time I cool it through its critical temperature, but I do not generally expect it to be the case that the direction it picks for its magnetization will be the same every time, and indeed in ideal cases, that direction could be completely random, although there are footnotes here about the crystal structure and so on, about which I will say nothing. To give a final example, which I won't discuss, but is quite topical, of course, there's been this Higgs thing going on. Well, it's been going on forever, of course, but it's in the news now, which obviously makes it much more important. And in a sense, the surprising thing about the existence of the Higgs boson is not that it tells us that the particle is there. It's that it tells us that we are living in a superfluid. So one of the fields around us, which is this Higgs field, has already broken a rotational symmetry that it had at high temperatures, and at some point during the cooling of the universe, this field went superfluid, and this is why the weak nuclear reaction is short range, which is surprising, and I don't propose to say much about it. I prefer to analyse the more prosaic examples, but it's interesting to note that actually, if we talk about matter, the existence of a lot of what commonly goes under the name of matter is in fact a result of a sequence of symmetry-breaking transitions that have happened since the early universe. The transition where light decoupled from the particles, the transition where the particles formed into nuclei, the transition where the liquids set into solids, have all been necessary to get this jug of water here now, and to make it keep its shape, which is very surprising that one of these transitions has led to objects that have shear rigidity. Okay, so those are my examples. Buridan's ass, Euler's strut, spontaneous magnetization of a magnet upon cooling, and I gave a fourth example, which is the spontaneous symmetry breaking in the Higgs field, but we won't talk about it again. So the question is, how is this possible? Because it seems on the face of it implausible that a system which has a certain symmetry perfectly can evolve simply with the passage of time, or the increase of pressure, or the change of any parameter which preserves that symmetry, into a system that breaks the symmetry. In layman's terms, how does the strut choose which way to buckle? How does the magnet choose which way to magnetize? How does the donkey choose which bale of hay to eat? Now, there is a standard answer that's given to this when such questions are discussed, but before pointing out what the standard answer is, I think I'd like to point out how rarely such questions are discussed, as a matter of fact. So it's an interesting feature of this domain of many-body physics that actually the nature of the calculations often elides this question of what causes the symmetry breaking. What one does instead is to show that at temperatures above the critical temperature, there is a single stable equilibrium state of the magnet, and that is to be non-magnetized. And at temperatures below the critical temperature, there's an infinite set of stable equilibrium states, all of which consist of the block of iron being magnetized, but magnetized in different directions. So actually, if a typical workaday theoretical physicist is asked to give a calculation that shows spontaneous symmetry breaking, that's the kind of calculation they will give. They will show that above the critical temperature, the stable configuration for the ion is to be unmagnetized. Below the critical temperature, the stable configuration is to be magnetized. And all of these calculations are done under the framework of thermodynamics, which implicitly actually has already left the system for an infinite amount of time to reach its stable state. So the question is not so much answered by these analyses as not asked. And it is taken for granted that if a ball is at the top of a hill at midday and at the bottom of a hill at 1 o'clock, then some dynamical process caused the ball to roll down from the top to the bottom, and maybe we don't care that much about what it is. But if pressed, there is an answer that people converge on. And the answer they converge on is what I should call the stray field explanation. And this is a name I've borrowed from the answer that's given in the case of the magnets, but you can imagine versions of it elsewhere. The stray field explanation says, okay, you're in a laboratory, and your laboratory is in a building, and your building is in a country, and the country has radio masts, and those radio masts broadcast radio 2, and those broadcasts are oscillating magnetic fields. Magnetic fields influence the magnetization in your sample, and so the statement that all directions are equivalent at the point where the transition takes place is just never literally true. So there is some stray field, some magnetic influence that has permeated your laboratory from outside, and that has in fact, in a given run of the experiment, selected the direction in which the magnetization will point. And of course, to you that seems random. because there's a lot of complexity there. You don't know what Terry Wogan's saying. I have no idea if Terry Wogan's still on radio too. You don't know what Terry Wogan's saying at the given moment, so you don't know exactly what the magnetic field is doing, and so to you it seems random. But of course, the point is in that explanation that it isn't real. There is something you could have known about the world which would have told you the direction in which the sample was going to magnetize as it went through the transition. So this is an account in which we say that what's really special about the critical temperature is that it renders the magnet very susceptible to very small influences on its behavior, which would normally be negligible. And of course one can give similar answers in the other cases. One can say, well, Buridan's ass may currently be standing symmetrically between the two bales of hay, but presumably the bales of hay are not precisely symmetrical. Even if the current situation is symmetrical, the ass will have approached this center point from one direction or another and may remember that, so may prefer to go on moving in the direction that doesn't involve turning round. There's always, in some sense, something you can say about why the symmetry is approximate rather than exact. Okay, and obviously Euler's strut is similar. The rod will buckle where there is a defect in the material. The material of the rod is bound to have some defect. That defect will already break the symmetry, and all we're doing in applying this heavy pressure is exposing that defect in the material in a way that was not noticeable at ambient pressure. So that's, as I say, what I call the stray field explanation. I'd emphasize that it's rarely proved that this is the case. And it's rarely possible to do very direct testing of whether this is the case, except, of course, applying such a large field as the system goes through its symmetry-breaking transition that it magnetizes along that field. That demonstrates that the field couples to the magnetization, but it doesn't actually demonstrate that it was the coupling of a stray field which picked the direction in the absence of anything else. But what I'd like to talk about in the last few minutes of my part is an intriguing experiment, and this is a real experiment, which appears not to fit this description. It appears to be a case where symmetry breaking could have happened, according to our stray field understanding probably should have happened, and yet in fact does not. And so this is an experiment that shows the phenomenon called super radiance. And essentially the experiment is this. Imagine that I have a cavity, and at either end of the cavity I have a pair of good mirrors. So what the mirrors do is more or less trap light in the cavity. They don't actually, they leak a little bit, but to a first approximation they trap light in the cavity. And I trap, somehow, a large number of identical atoms in the cavity as well. Now the nice thing about quantum mechanics is that when I say identical atoms, as far as we know I mean it. It is possible to prepare a system of identical atoms in such a way that, at least according to orthodox quantum mechanics, there is no experiment you could do to discover which atom is which, and indeed this notion of which atom is which is meaningless, which underlies such phenomena as boson-Einstein condensation and superfluidity and so on. So I prepare these atoms and I excite them all. Right? I mean, obviously atoms have many, many possible excited states they can be in, but let's pretend for simplicity that these only have two states, a ground state and an excited state. So I prepare all the atoms in the excited state and I put them in the cavity. That initial configuration is symmetric in the sense that all of the atoms are excited, which means that swapping any pair of the atoms doesn't change it. And then I say, what happens next? Now, an atom in free space will spontaneously decay from its excited state to its ground state due to its coupling to the surrounding electromagnetic field, and it will emit light. So one might think that what each of these atoms will do is simply to decay, emit light into the cavity, the light will sit there for a bit and then leak out through the mirrors at the end. Now we can make a prediction about what the intensity of the light emerging from the cavity is as a function of time in this case, because it's just like radioactive decay. A load of independent particles Apologies for a graph with time on the axis. So if I predict the intensity of the emerging light as a function of time, I will just predict a regular exponential decay with some characteristic decay time which I can calculate from atomic physics. Interestingly, this is not what's observed. What's observed, apologies for the poor hand sketch, is a behavior like this. And this is the phenomenon, the existence of this peak, which is referred to by the term superradiance. Now, what's going on? Well, the answer appears to be that this system is not breaking the symmetry between the different atoms in the cavity. So, if I model the system quantum mechanically, there's a way of representing it in which I consider only the dynamics in which all of the atoms evolve in precisely the same way. And of course, this is an option that's open in quantum mechanics. It is not necessary to emit light for a single atom to decay. One can have an evolution of the system where each atom is always in a superposition of the excited state and the ground state. That superposition is the same for all the atoms, and then over time that superposition gently evolves so that there is more of the ground state and less of the excited state, but always retaining this perfect symmetry under interchange of the atoms in question. If one does the calculation, and that is actually what quantum mechanics predicts in this case, one discovers that this should be the pattern of the emitted light. The coherence between the atoms is essential in causing this to occur rather than this to occur. And I emphasize again that what is experimentally observed is the case in which the symmetry under interchange of the atoms is preserved, not violated. In a certain sense, then, this is the equivalent of the donkey going into a superposition of going to eat one bale of hay and going to eat the other, or the strut going into a superposition of buckling in all possible directions, or the magnet going into a superposition of having magnetized with the magnetization pointed in all possible directions, and it is experimentally diagnosable that this has happened. So the puzzle that leaves, I think, is, what about the stray field explanation? It is still the case that at any given moment, not all of the atoms in the cavity are in the same position. And therefore, if I believe this statement that rather than following the symmetric path, the system will be perturbed by very small influences into one of the non-symmetric options, I would have expected the same stray field that picked the direction of the magnetization for the magnet to pick an atom in this system which was going to be the first one to decay. So I might have said that this was the more likely outcome, not because the clean theory predicted it, but because I know from other relevantly similar cases that there is always some stray field which breaks the symmetry. In the superradiant case, that appears not to occur. So let me just raise, in my last 2 minutes, a couple of points that I think might be interesting to talk about in the discussion, and then I'll turn over to Patrick, who will tell a parallel cautionary tale about indeterminacy in philosophy, and also in physics. So my questions are essentially 3. 1, if spontaneous symmetry breaking is not in fact ubiquitous, as the superradiance example suggests it isn't, why do some systems do it and others don't? 2, an interesting feature of the superradiance case is that not only is the starting state symmetric, but the end state is symmetric. That's not the case with the strut. So the starting state is an unbuckled rod, the ending state is a buckled rod, and the buckled rod clearly violates the original symmetry. However, in the superradiance case, the starting state is all the atoms excited, which is a symmetric state, and the ending state is all atoms in the ground state, which is also a symmetric state. So is that an important feature? That superradiance involves the evolution from a symmetric start state to a symmetric end state, where the other examples go from a symmetric start to an unsymmetric end. And finally, touching on questions of teleology and teleonomy, if that is the important difference, how does the system know when the radiation begins, when the pattern is already different, that the end state it's heading for is a symmetric one?
Say the last one again, please.
And so the last one was, if it is the case that the important thing about superradiance, the reason it behaves differently from the others, is that the end state is symmetric as well as the starting state being symmetric, how does the system know when it starts emitting the light that that's the case? And on that slightly upsetting note, I shall now knock over my last bottle of wine, leave the party, and hand over to the chap with the dustpan and brush.
James Latham, my erstwhile colleague at Bristol and friends, has a metaphor for the relationship between philosophy and physics, which can be described as follows. Physics sits on a hill, sort of golden temple of truth and intellectual integrity. Analytical metaphysics is some slum down the road, and there is a sort of passage of information between the two. Interesting stuff comes down the hill to the slum below, but nothing of any interest or worth or value ever exits from the slum analytic metaphysics. I publicly likened his views on metaphysics to the impact agenda in academia, saying, well, his views are, well, if it has no impact in analytic metaphysics, we should get rid of it. Of course, James is also famous for being an anti-impact agenda person. So I'd just like to say, I've sort of emerged from the slum, but actually I think there's a lovely little pathway between the two places, and this is exactly what we've ended up. I'm interested, I don't think I can clip the songs here. Can you hear me?
Yes.
Yeah?
Yes.
Do we have a rug so I can just wipe that off?
We use paper towels for this function, straight.
So spontaneous symmetry breaking, a notion in physics, indeterminacy, a notion that's much discussed by philosophers, also philosophers of physics, quantum mechanical indeterminacy being one of the prime examples. So is there an interesting connection between these two things which will help us understand this better, or this better, or both of them better, and what is the nature of that relationship? Well, spontaneous symmetry breaking seems to have a reasonably good definition in the literature. A system will exhibit spontaneous symmetry breaking when it will go from a high symmetry state to a low symmetry state as a function of some change in some parameter, temperature, over time. And then there's an interesting extra clause which is crucial to distinguish spontaneous symmetry breaking from explicit symmetry breaking, where there doesn't seem to be any explicit additional asymmetric input which is as it were causing the symmetry to be broken. So we look really hard and we just can't see anything else going on. Maybe there is something else going on, stray field explanation, but at least if we look at the system, it doesn't seem as though it's there. Maybe we're not being hard enough, or the other option, of course, we'll talk about that, is, well, there isn't anything there. So what I want to do is, so Chris has got various examples of spontaneous symmetry breaking. Indeterminacy, you can think of indeterminacy like cancer. It comes in many different sorts of varieties and kinds, and some is a lot more toxic than others. So what I want to do is just look at some cases of indeterminacy to see if we can come up with an analysis of indeterminacy which is very much like the definition that's given for spontaneous symmetry breaking. Then at least we're in the ballpark of saying, yes, there is a connection, and yes, hopefully there'll be some mutually illuminating walking up and down the street between physics and metaphysics. One example of indeterminacy which you might consider is I go to the shop and I notice that there's an offer on for toothbrushes. Buy one, get one free. So I take them home. This is great. I buy one and I get one free, so I take them home. Then it occurs to me, which one did I buy? And which one did I get for free? It begins to really puzzle me. I phone up the manufacturers, I ask the shop. There doesn't seem to be any explanation which explains that it was this one that I'm holding, the one I'm using now, rather than the other one that's still stuck in the packet. And they seem relatively symmetrical. The toothbrushes are constantly identical, more or less. There isn't a little sticker on one which says, this is the free one, and so forth. So you might think, oh, that's a case of where the underlying facts are symmetrical, but there's some other facts where the symmetry seems to be broken, that the system as a whole, you can think of that as the latest state, has a property whereby the symmetry is broken. One is for free. When they were first manufactured, they didn't know whether to run that offer or not. But later on, they seem to acquire this property, one being for free and one being for purchase. That isn't, of course, a very good exemplar of indeterminacy, because you can just paraphrase. You fool! Imagine writing an AHRC grant for this and saying, I'm going to base the rest of my career on this. The reports come back and say, the toothbrushes you bought for £1, one was 50 pence, and guess what? The other one was 50 pence. That's the answer to the problem. So that isn't a very good case to begin with. There's a kind of faux indeterminacy at work. Another case would be a very, very famous case called the ship of Theseus, discussed by Hobbes. You have a ship, and the ship slowly gets renovated over time. So at the end of some process of renovation, you have another ship. So this is a system which evolves over time. Call that the A ship. That B ship. But some rather ingenious shipwright thinks, oh, well, they're always over-renovating this ship. I'm going to save the planks, save the bits, the masts, the spars, and so forth. And every time we go back to port, I'm going to leave them in port. And then one day, after they've renovated everything, I'll have all parts to build my new ship. So in fact, part of the process of renovation and collection and reassembly allows you to generate another ship. Now this is the ship of Theseus. It seems, intuitively at least, that these things aren't identical. At the end of both of these processes of renovation and reassembly, we are left with two things and not one thing. So they're numerically distinct. The question then arises, well, which really is the ship of Theseus? Now, of course, you might be just tempted to say, well, this is the ship of Theseus, and this is the one that's got the greater core. This is just some, well, this has all the original parts. You could have disassembled, part of the renovation could have involved complete disassembly here, maybe even some swapping of the parts that were kicking around by some folks trading in ship bits on the key side and so forth. And so what you can do is start to bring these two options into symmetry. Then it looks like it's indeterminate whether A equals B, and indeterminate whether A equals C. These two options are symmetrical. Nonetheless, logic dictates, if the ship exists at all at some future time, there's one and only one ship. It's either this one or it's this one. So the symmetry has to be broken by logic in this case. Of course, what's interesting in indeterminacy cases is that you get the result that one and only one direction or polarity or whatever you like is chosen, but you might not know which one it is. In fact, it might be fully indeterminate. One and only of these ones is chosen, but it's somehow indeterminate which. I'll come to a case where you can find out which is chosen in a second. So there's a kind of symmetry here. These two options are symmetrical, but of course logic dictates that there's only one and only one Superposition. It's either this one or this one. But which one is it then? One hallmark of indeterminacy is actually uncertainty. So one question, general question that you can ask on both sides of this putative equation is, where is the source of uncertainty? You don't know which way, which polarity is going to be chosen. You don't know which way the strut is going to go. There's some uncertainty in the initial state of the system about how it will evolve. There's always uncertainty and ignorance about indeterminacy cases. Which is the share? Is it B or is it C? Can't be both B and C because they're numerically distinct. That might not be a very good example of indeterminacy. You might think, oh, well, come on, these are not qualitatively identical. Maybe there's some stray field sort of explanation. Maybe there's something about the way in which this was renovated, something about the way in which this was reassembled. There's always going to be one molecule somewhere in the universe which is going to break the symmetry. So maybe this is not a good case. A further case from so what happens in the indeterminacy debate, like I say, it's a bit like cancer, is that you get lots of different examples. So we get the toothbrush case, we get the Superposition, something I won't discuss but was mentioned in the introduction. The vagueness debate in philosophy is enormous. Another case is, you may have heard of these things, lilac paradoxes. And these, of course, form a family amongst themselves. One of these paradoxes is called the no-no paradox. Supposing I write a sentence on the board as follows. The neighboring sentence is not true. How do we evaluate that sentence? Well, given that there is no neighboring sentence, it's a non-referring expression. The neighboring sentence doesn't refer, so it doesn't really express a proposition. There's nothing for it to refer to. But supposing I write a perfectly symmetrical sentence up there with it, the neighboring sentence is not true. Okay, it's not quite symmetrical in the sense that my handwriting is worse on this one than that one, but bad in both cases, and so forth and so forth. But you can see that depending on how you want to individuate sentences, you want to say, well, this is the same sentence type, perhaps, or a tokening of the same type. So they're relevantly symmetrical. We're always going to have this notion of relevantly symmetrical. In Burin's ask case, you might find slight differences, and so forth. How are we going to evaluate these sentences given that they are meaningful? Looks like we've got four options. They're both true. That's one symmetrical case. They're both false. That's the other symmetrical case. Of course, there are two asymmetrical cases. True, false. False, true. But our background metaphysical prejudices are thinking, well, the underlying facts are all perfectly symmetrical. So when it comes to evaluating whether or not these sentences are true, we can only really surely end up with either this one or this one. False, false. Those are the only two live options. But if you think about it, suppose that the two sentences are true, then what they say is the case. If what they say is the case, then the sentences are both not true. So if they're both true, they're both not true, contradiction. Oh, they must be both false then, or both not true. If they're both not true, then what they say is not the case. If what they say is not the case, then the sentences are both true. Contradiction. They're both true, they're both not true. If they're both not true, they're both true. Contradiction either way, so the symmetrical assignments of truth value are ruled out. We're left with the asymmetrical assignments. Oh dear, that's a breaking of symmetry in some relevant sense. The underlying facts, as philosophers sometimes like to call it the subvening facts, are perfectly symmetrical, but we're getting an asymmetry in the supervening facts namely a difference in truth value, what the hell could be bringing that about? You stare at this sentence, can't see anything. You stare at this sentence, can't see anything. So there's a symmetry-breaking phenomenon there. Even then you're not convinced. Maybe you think the subtle influence of context is playing some role here. Maybe in the very act of evaluating a sentence to be true, you somehow change the contextual parameters which are somehow determining whether or not a sentence is true. And that's a huge topic in the philosophy of language, the influence of context on meaning and truth. So you might say, oh, I'm a contextualist, and what this shows is that there's some kind of Heraclitean problem here. The very act of evaluating these things can destabilize the system and break the symmetry and allow us to choose a differential assignment. Of course, that's, I think, going to be a slightly tenuous explanation. I don't say you couldn't do that. The other option is to say, well, we're going to reject a platitude in common sense metaphysics. Actually, the platitude closely related to the metaphysical presupposition that the straight field theorists are really using in that they think, well, something's got to be breaking the symmetry, some break, Terry Wogan or something. The platitude in metaphysics is that truth, as philosophers put it, supervenes on being. Whether or not a proposition is true or a sentence is true depends on what the world is like. But if the world is relevantly symmetrical, you'd expect the truths to be relevantly symmetrical. That's what we don't get here. So it looks like if you start to take indeterminacy seriously and think that it's a deep phenomenon, you're going to give up on the so-called platitude that truth supervenes on being, or as it were, the truth facts about which sentences are true are determined by the way the world is, not the other way around. So supervenience gets lots of different analyses in the philosophical literature, but in its so-called global form, if you've got a world W and a world V that are identical in some underlying respect, then they'll be identical in the higher level facts that the supervening facts. So if you get a difference up here, you get a difference in truth value. So if these sentences really are different in truth value, then there should be some difference in the sentences. There should be some difference maker. And I think it's this metaphysical presupposition which is really behind the straight field theorists' search for, though as yet they haven't found any concrete examples, for the straight field explanation. So they're deploying, I think, metaphysics in their reasoning. Finally, how am I doing for time? 10 minutes. Finally, let me pick an example which is a bit closer in the philosophical literature to the cases that Chris considers, and that's the so-called open future. And in fact, considerations of the open future do really bring physics, philosophy, and theology together, because theologians are particularly interested in the open future. I mean, one of the reasons why theologians are interested in the open future is God's grace. I mean, how is God going to give grace to you? How's God going to have God to do that? God would need foreknowledge of what's going to happen in the future, but then that would seem to imply that the future is closed, and so there could be no freedom, and that caused all sorts of theological disputes in the medieval age and right up to the present day. What is it for the future to be, in some sense, open? There are many different ways of thinking about this, but one increasingly common way, and you may think this is metaphysically extravagant, is to have a so-called branching time model of the world. The simplest one of those models is just the three-moment model. So you have a moment M1, a moment M2, and a moment M3. History H1 is composed of M1 and M2. History H2 is composed of M1 and M3. And so both of those histories overlap at M1. Moreover, in some of the models that philosophers give to this, they think of these as not being ersatz or sort of fake options. These are concrete things. So reality is actually fragmented into a tree of concrete possibilities which are before you. Here you are at M1, and you're wondering about whether or not it will rain. Does it rain here? No. So at M2 it rains, at M3 it doesn't rain, and let that be where time just ends. Simple 3-moment model. Now if the future is open, to say that the future is open is to say, well, all the facts that obtain here are insufficient to determine that things go this way rather than this way. So all the laws of nature, the initial conditions and so forth, get as much information, get as much knowledge as you like, you won't find out which way it's going to go because somehow the underlying mechanism isn't sufficiently detailed to choose between M2 and M3. So philosophers worry about the truth values of things like propositions or sentences. It will rain tomorrow. That's what Aristotle originally worried about. But nonetheless, you can see it's got a similar structure to the ship of Theseus example. It looks like there's a high symmetry state here that the way the future will turn out to be is symmetrical between two options. But as time flows, if you want to look at that, well, this is actually a static model, but from a later perspective, we're at the low symmetry state. Interestingly enough, it becomes perspectival. From here you think it's the kind of Spartacus problem. Phew, I'm the one that survived. Well, you're also here. No, I'm the one that survived. But logic dictates that either it will rain or it won't rain. Or it's not the case that it will rain. Either it will rain or it won't is a kind of quasi-tautology, which you can derive from logic. So if you think there's one and only one future, then there's only one way that things can turn out. So despite these history 1 and history H2 being qualitatively identical, no difference between them. Well, this is the Rennie case, but relevantly symmetrical in terms of what the facts are going on down here. One of these is going to get picked. Now, stray field explanation would be, oh no, there's something creeping in. Something creeping in, which is making the world plump this way rather than this way. The other option is to think, no, there's a kind of plumping for free. That one and only one of these future histories gets picked as the ref. So if I start using the word the future, it's a singular term. It refers to one and only one thing. It picks out one of those histories, in the simple case H1 or H2. So it refers either to H1 or H2, but it's indeterminate which. On this model of indeterminacy, that consists in a deep failure of symmetry. That facts about future contingents, facts about what the future refer to, are not determined by all the facts that obtain at M1. You get a failure of truth to supervene on being. The higher level facts about truth, fail to supervene on the low level facts. The stray field explanation is no. There are some asymmetric input at this point which would choose between H1 and H2. So the faux case, toothbrush case, paraphrase, get rid of that. Ship of Theseus case, well, maybe there's always something which you can pick, some relevant difference which will break the symmetry. The no paradox case, maybe the influence of context, maybe we can have a subtle theory about how that works which will break the symmetry. Much harder to think about how that might occur here. So this case, because of the evolution over time, I think is the closest philosophical case to the examples that Chris might be considering. Finally, I just want to say something about indeterminacy. As I've said, you can look at the exemplars. So the definition that you give, you say something like, the definition would be, hey look, haven't we got some supervening facts, some subvening facts, the A facts, and these are all symmetrical? And haven't we got some higher level facts, some B facts, where they're relevantly asymmetric? But oops, it looks like the only thing that could have brought about these facts or these facts. But how can that be when we've got symmetrical inputs and we've got some asymmetrical output? How can that be? Well, the extra clause in the definition here is just, well, and there's no apparent additional set of facts which goes into the subvening base to determine that the B facts obtained. It might be that there are some extra facts there, it's just that you don't know what they are, how they work, what the underlying mechanism is. So you can give a definition, but maybe the definition is not a sort of equivalence, maybe that indeterminacy is a broad phenomenon and spontaneous symmetry breaking is just a range of special cases of this broader phenomenon. But you might come along and say, no, I completely disagree that this is happening at all. Go back to the no-no paradox. You might want to say, well, there is absolutely nothing wrong with thinking that the sentences can be both true and false. So one thing that enforces symmetry, enforces the breaking of symmetry in the indeterminacy cases is classical logic. Either it will rain or it won't rain. A proposition must be either true or false, or it can't be both true and false. You won't give up on all of that, and it's a bit like the super-radiance case where you get the superposition of sort of being in all states at once. You could have a view of indeterminacy whereby you think actually future contingent truth values are both true and false, or the no-no sentences are both true and false, or A equals B and A equals C are both true and false. And so you give up on classical logic. Giving up on classical logic allows you to get symmetry back, and you don't get symmetry breaking at all. It seems very close to the cases. The cautionary tale that Chris tells, I think, is in the super-radiance case, wouldn't we expect the stray field explanation to be cutting in there and causing the symmetry to be broken? We're not finding that. So that should make us suspicious. This is an empirical argument, in effect, I take it, suspicious of whether or not the stray field explanation can be brought to bear on the Euler strut in the other cases. There's a sort of intermingling here of common sense metaphysics and empirical explanations of things. But I want to just stress that presumably stray field explanations are deploying this underlying common sense metaphysics. Things just can't happen for free. You just don't get free facts. Fields of supervenience involve free-floating facts. You just get these B facts obtaining. Hey, they must be determined by the A facts. No. The A facts don't determine the B facts. You get free-floating facts. If you allow for that, and lots of theorists in the indeterminacy debate might well do, once you get exposed to enough of these examples, you start to think, oh my God, what is determining this breaking of symmetry? Nothing at all. Just get it for free. Then you've shaken the tree enough to be on board with Chris's cautionary tale. Thank you.
Okay, thank you both. That was really interesting. First question to Guido. Mic there.
Okay, I've got one brief comment on radiance, and then the thing I really want to say is, have I got time for both, or shall I skip the brief comment? Aaron?
Sorry?
But brief comment to radiance, and then the stuff I really want to say. Shall I go straight to that, or have I got time?
Yeah, so you can have to.
Okay, small comment about superradiance. In all the other examples, we do have different final states available. That seems to me in the case of superradiance, because symmetrization postulate is a fundamental restriction on available states. We don't have these different possibilities.
I only have genuinely different intermediate states available.
Aha, okay.
Now, I agree with you. There is a unique end state, and that was my reason for mentioning that discrepancy at the end. And then the question that raises is, at the point where the time evolution starts and the radiation starts, how does the system know there's going to be a unique X?
Okay, let's talk about this later. It's becoming technical. So, here's another example. Measure stone Gauge measurement. You've got a symmetric case. You've got superposition of spin up and spin down, equal superposition of spin up and spin down. You get only one result, up or down. Now, the stray field explanation in this case tends to be unpopular. It's called hidden variables. So you're either left with genuine collapse, there's really something random happening one way or the other, or the other alternative in philosophy of quantum mechanics is error. So if you do have the superposition of both, but we are stuck in, well, and we observe sort of both results, but yeah, we have split too. We are part of that superposition. Now, you think it's a plausible diagnosis, at least in the quantum mechanical cases, in which we have splitting symmetry breaking, that indeed it's the same kind of thing. We have a quantum mechanical collapse happening, or a splitting into different worlds, or the less popular option, there's hidden variables.
So briefly, the question is spontaneous symmetry breaking an instance of quantum measurement?
Or something like that. Measurement will equal zeros or something like that.
I guess I wouldn't know how to rule that out as an option. I mean, mainly because I don't know what quantum measurement is. The fact that I seem to see... The reason I'm a little hesitant about it is because the Euler-Strutt example just feels so classical. I'm inclined to say that I'm inclined to respond that they're not the same. And the reason I'm inclined that way is that there seem to be classical cases where I'm sort of, maybe this is prejudice, but where I'm not inclined to believe that in the very early stages of the buckling, Euler-Strutt is in a superposition of all buckling directions, and then that superposition collapses by whatever mechanism superpositions normally collapse. But I couldn't prove that.
Great, so next question.
Well, just to sink the ship of Theseus once and for all, it seems to me that there isn't a fact of the matter which of the subsequent ships is entitled to the title of ship of Theseus. It just depends on how you define what is the same ship, whether it's got the same material components, which is the one that's been assembled in the shipyard from bits of the other ship, or the one that has some kind of continuity from a free club point. So it seems to me there isn't a fact of the matter there, so that shouldn't worry you as much perhaps as, well, I think you do set it aside, but it's one that's easily buried, isn't it?
Well, when you say there's no fact of the matter, if I don't have the competing ship C, do you think there is a fact of the matter that A equals B, or do you just don't think there is a sufficient set of individuation conditions for judging whether or not an ordinary object persists over time?
Absolutely. I have to say, which of you can claim to be the true ship of Theseus depends on the criteria, whether it is the same material components or whether it is some kind of continuity, so you can track the ship as it loses bits and replaces them. So no, it's purely a definitional matter, really, isn't it? I don't think it is, or perhaps you think underneath the definitional problem there's a serious metaphysical question.
I'm kind of on board partly with what you want to say, in that if you look at all the different philosophical theories to do with persistence over time, you find that they compete. They're actually in tension with each other. But the thought then is, well, perhaps some of these theories are latching onto our ordinary concepts of what it is to persist over time, one facet of it, and the other theories are latching onto, guess what, another facet of it. And it's not that there's no fact of the matter, there's not too few instructions about whether or not to call the ship of Theseus A or B. There are too many instructions. It's a kind of over-determination phenomenon that our ordinary notion is incoherent. So lots of natural language, lots of ordinary ways of thinking are just incoherent. Then there's the question about what you do with that. I mean, do we do we clean them up? Or would that be an unenviable task and unnecessary and make bumping around in the world too difficult? But so I'm kind of sympathetic to what you want to say, but I wouldn't see it as a gap phenomenon. So there isn't enough to say about what's going on here. I mean, you can get a kind of second order gap. If I have a sign which says go left, diversion go left and diversion go right, there's a sense in which I'm giving too much information, but I'm also given a cancelling out phenomenon that I'm given no information at all once the two things are competing. So I'm sort of sympathetic to your take. It just depends on how you get to the point that you're out.
Okay. Questions? There's one up at the back.
This is for Patrick. How does philosophy, how does it contribute to physics in the sense, how do you rule out the stray field theory from a philosophical sense?
I think philosophy can contribute to physics in a number of different ways. I mean, part of what I was trying to do today is just to reveal that physicists, I mean, Chris was clear about this, I think, that physicists do have metaphysical views. So why seek an explanation along the lines of the straight field explanation when you haven't actually found any concrete instances of that explanation working in a case of the breaking of symmetry? Well, what's guiding your thought there is a metaphysical view of the way in which higher level facts, if you like, are determined by the lower level facts. So what philosophy can do is reveal what that is, articulate it in various ways, critique it, but at least put it on the table for scrutiny. I don't have the view, by the way, that philosophy can just proceed from the armchair completely independently of physics. Philosophy has to be informed. I'm on board with Lehman in that respect, that an uninformed metaphysical picture is going to be hopeless. That if philosophers can't deliver help to physicists, then a lot of what they would do is nugatory. But one shouldn't have the kind of impact view that Lehman has, that tell me what your impact is right now, because unlike the logical positivists, Lehman has the view that I can't say a priori from the armchair that analytical speculation in metaphysics won't work, because we know that in mathematics that could have been accused against pure mathematicians speculating against some arcane field in mathematics, which later physicists have gone, oh my god, I really need that to help me construct my models. So I think the dialogue between philosophy and physics can be indirect. It can be neighbours talking to neighbours or meeting halfway in a venue like this. But that's the general picture. But the concrete example is philosophers are very interested in symmetry. They're very interested in the Leibniz's identity of discernibles. They're interested in quantum indeterminacy, what a superposition is, what collapse might be. I mean, collapse is related to this kind of breaking of inconvenience idea and so forth. So,
just one other thing. So, in the case of the stray field theory, what you're saying is that philosophy can't rule it out, but it can question it. It can sort of.
Philosophers are certainly not from the armchair. We're going to say all stray field explanations can't happen. That's an empirical question which they await results from physics to tell us about. But there's a question about articulating why you would want to believe in the stray field explanation in the face of never having found a concrete example. What's informing your hunch there? The stray field explainer is informed, I think, by metaphysics rather than physics at that point. So just pointing that out reveals a metaphysical presupposition that they have. Let's articulate it, let's critique it, let's bring it into the light. Maybe there are different versions of it. Maybe once we bring it into the light, we can hone it such that it becomes more empirically testable, and indeed we will get a successful stray field explanation in various concrete cases.
Thanks.
I maybe just have a quick note on that. I think there's another problem with this view that we don't really need the interaction, is that sometimes what people seem to have in their heads is the idea that, in the end, physics will take the data anyway. So, we're going to see the answer to this question sooner or later, so why not just wait until those data are taken? But I think that's a misunderstanding of the way physics operates or ever could operate. I mean, the number of possible experiments you could conceivably do is just unimaginably large. And in actual fact, in many cases in the history of physics and the other sciences, the motivation to try and do a particular experiment has come from rather philosophical reflections on where the theory or the picture of the world seems to have holes. And Einstein and de Haas did their famous experiment about the transference of spin to orbital angular momentum and the rotation of the cylinder because they thought there might be a conceptual problem about thinking that spin and orbital angular momentum were the same thing. So often actually the experiments that tell us the most arise from precisely this kind of discussion and are honed in this kind of discussion to try and nail a conceptual issue that otherwise seems vague.
We have another question.
Seeking to ascertain that there's no experimental test of the stray field theory. We do get unusual states in physics where matter is in a form that's unstable and it needs a trigger, which is very tiny. And in fact, the old bubble chambers in physics used to work on that principle. You used to have a superheated fluid, but because it was all clean and symmetric, there's nothing to trigger a boiling of the liquid until a particle actually went through. So would that count as a case of a stray field theory? Do you think?
I think not, and the reason I think not is because that's actually a case of nucleation, which is not quite the same. So in the case when a vapor is sort of ready to turn into a liquid, that transition is, the technical term is first order, by which I mean that when the vapor goes to the liquid, there's a discontinuous change in density. So both the vapor and the liquid are sort of locally stable if you don't disturb them too much. So in a sense that's not stray field, because the disturbance has to reach a critical strength before the transition from one state to the other occurs. So if I imagine I have a working cloud chamber and I just turn down the charge on the particle, before that charge reaches zero, the cloud chamber will become unable to detect it because it's now not a strong enough nucleation center. Whereas somehow the principle with stray field is it could be as weak as you like, because what was previously a stable, unmagnetized state has become genuinely unstable to arbitrarily small perturbations.
Okay, so I think we have time for one more question.
It's probably a question for both. I wonder if we need a distinction between relative symmetry and absolute symmetry or similarity. Something can look symmetrical from the naked eye, of course, under an absolute regularities within themselves. So our actual judgments of similarity or symmetry are all relative to certain respects or certain operations. Absolute symmetry or similarity would require godlike omniscience, which not even physicists have.
You want to take it on or not?
I mean, the limit case of symmetry would be identity. So you might get principles which are like Leibniz's law, and then you say, well, A is identical to B if and only if they share all their properties in common. One way of relativizing is just to restrict the range of that quantifier. To say, well, it better be intrinsic properties, not extrinsic ones, or it better be some relevant range of properties. When people, all of these, there's a whole bunch of relations in this area. One is indistinguishability, understand relation. What they do is they relativize to the ways in which the objects are presented to human observers. So something can be indistinguishable under one mode of presentation, but distinguishable under another, or discriminable under another. So I think you're absolutely right. Identity doesn't, the standard view of identity, numerical identity, is that it isn't a relative notion, batching each. But the standard view about these identity-like relations, indistinguishability, maybe indiscriminability, or maybe symmetry, is that there's relativization has to be built into the specification of what the relation is. Absolutely.
I maybe just had a couple of thoughts on that. So I certainly accept from the philosophical standpoint that is an important distinction. However, there is some evidence, apparently, in phenomena such as Bose-Einstein condensation or the Pauli exclusion principle. And these are explained, at least by the current quantum theory, in terms of the literal indistinguishability of the constituent particles. And they make physical predictions that only hold if the physical particles are literally indistinguishable. So it's part of the modern conceptual framework of quantum mechanics, as applied to many particle systems, that actually there is such a thing as indistinguishability in principle. And of course that conflicts with our traditional classical notions because, when I assemble particles into an aggregate, I can always, in principle, follow the particles that were assembled in such a way as to find out where particle 1 went and where particle 2 went. But of course the claim of the uncertainty principle is that that becomes impossible in quantum mechanics in principle, not just in practice. And there do seem to be physical phenomena in the world that flow from that exact indistinguishability. The other observation is that it would feel a very unsatisfactory position to be in if we had no way of organizing physical influences in order of importance. This was Einstein's problem with correlations at a distance in quantum mechanics, that it seemed to suddenly make something which you ought to be able to ignore, something you couldn't ignore. So there is a procedure of saying, well, let me look at, for example, at the solar system. The largest gravitational potential energy is that between the Sun and Jupiter. So this is where I start my description. I work out the orbit of Jupiter around the Sun. The next largest correction is that between the Sun and Saturn. So I carry on this way, I establish the orbits of all the planets, and then I have these subdominant corrections due, for example, to the gravitational interaction between Jupiter and Saturn, which I hope, because otherwise I don't know how to proceed, I can treat as small perturbations to the solution I've already developed. So the worry about saying that there will never be actual symmetry in practice is that, okay, it's agreed that there won't, but then I don't know how to start building a theory if I might have to pay attention to all of these little aspects in which the systems differ but which I normally ignore.
Great. We'll have to stop there. Next up is coffee, but let's thank our speakers.